today, here we go, is a new section called the mean value theorem. And we'll tell you what that is, probably about number 3. But essentially, it's a theorem that allows us to tell something about possible values of the derivative and how to solve them. Now, to be able to use the mean value theorem, called MVT for short, in order for you to be able to use it, there are 2 conditions that have to be met. The first is that the function must be continuous on the interval a to b, and the second is it must be differentiable on a to b. And so they start off with a couple of very visual questions where they show you graphs and they say, would you be able to use the mean value theorem on this graph, right? So hopefully you're looking at question 1. Is that graph continuous? Yes. To remind you, the easiest way to think it continuous is start at the left-hand side. You can drive along this road. I know that's a kind of T-junction, whatever, but you can go from one end to the other. That typically means your function is continuous. Okay. Now, is this function differentiable? In other words, can you get a tangent line at any and all points on that curve?
Can you, is 0? Am I thinking of it being 0 at the corner?
You don't need to worry about the start and the finish, because the tangent line there would probably be a slope of 1 anyway.
Oh, I meant like the top.
Oh, the top there is not a 0.
Okay.
To be a nice curve to be 0. So what you've actually found there is the place where it's not differentiable. Right? Little house shape, not differentiable. So this function is continuous, but it's not differentiable. And so when it says, does this satisfy the mean value theorem? The answer is no, because it's not differentiable. And since it's not going to work, you won't be able to do that guy. Have I got the answers? I wish it wouldn't. Oh, it's got solutions this time. Okay. Right. Has that second function got a problem?
Yes.
Right.
As not
Right,
differentiable at a point.
Yeah, which would be probably 3. So isn't that answer going to be pretty much the same as the last one, right?
Progress.
So you can only use the mean value theorem if your function is continuous and differentiable. And in those 2 examples, the answer was no. So you say no and then D and E. So what we're now going to do is look at functions that you can use the mean value theorem. But we're going to do, that's the right one, we're going to do a special case. We are going to be doing what is called Rolle's theorem first. There are only 2 of them. Now, what Rolle's theorem says is, imagine that you have a function that is continuous and differentiable, right? And at x equals a, the height that it is, and at x equals b, it's at the same height. So can you imagine a function that starts off at that height and does some stuff and finishes off at that height? Your function, if it's going to be continuous and differentiable, isn't that the kind of shape it's going to have, right? Now, it could have a big hill, right? It could have a big valley, right? It could be squiggly lines. But that's essentially when you put those conditions on a function, that it has to be continuous and differentiable, and it has to start and finish at the same value, which we would describe as saying f of a equals f of b. If all those things are true, then Rolle's theorem says the following: there must exist at least one value of x, typically called c, such that the derivative at c is equal to 0. In other words, you must have at least one hill and or one valley. Does that make sense? That if you start and finish at the same height, I guess the only exception would be a straight line from there to there, but doesn't a straight line have a 0 derivative everywhere? So it's definitely at least one. That's pretty much Rolle's theorem in a nutshell. So let's show you how you apply it. Here is question 3, or a version of it. The function that we're going to do Rolle's theorem on is 3x squared, take away 6x plus 4. And we're interested in x from -3, -1 to 3. You wouldn't normally write this, but for the sake of notes, I'm doing it. This function is continuous on the interval 1 to 3. How do I know that? Aren't all quadratics continuous? There isn't one that isn't, right? I just know that. This function is differentiable on the interval -1 to 3. How do I know it's differentiable? Aren't all quadratics always differentiable? Right, there isn't a problem. You can find the derivative of any quadratic. Because isn't a quadratic just a big happy face or a big sad face? There's nothing really much going on. So you would go through those two without even doing it. You would just say, yep, I know it's continuous and differentiable. Now, this guy is A and this guy is B. So I'm going to find the value of the function at -1. And I'm going to find the value of the function at 3. And this one is the only one that you really need to check for. If you plug -1 in here, you're going to get 3 lots of -1 squared. Take away that guy, add 4. That's 3, add 4 is 7. 7 add 6 is 13. And then if you do the other one, it's going to be 3 lots of 3 squared. Take away 6 lots of 3, add 4. And that's 27. Take away 18 is 9. 9 add 4 is 13. So is it the third condition met, that the value of the function at the start and at the end is the same? In this case, 30. So once you have done that, your job is now to find the missing number C, or in some cases, 2 C's. So C, for instance, would be that guy there. Here is the function. Find its derivative. And according to Rolle's theorem, the derivative has to equal 0. It's really finding critical numbers, isn't it? Finding when it's 0. And so you get 1, which means your answer is 1. Now let me show you what that looks like in WebAssign. You see there's very little told to you. They don't say find this, find that, do this, do that. Don't they just say, hey, check that you can use Rolle's theorem and find the missing C. And we just found it, right? X equals 1, C equals 1. And if you go to this one, well, let's talk it through. Would you agree this quadratic is continuous because all cubics, I should say, are continuous? Aren't they also differentiable? Can you trust me that if you plug -4 into this function, you get the same answer as when you plug in 4. You can check it, but you do. Then aren't we left with finding when this derivative, right, when the derivative of this function is equal to 0. Now, though I'm not doing this one, wouldn't you end up with a quadratic if you differentiated that guy? So if you want it equal to 0, aren't you probably going to factor a quadratic and get 2 answers? And this is not correct, but I'm going to pretend it is. And the answers end up being -2 and 2. And that's what they mean by a comma-separated list. And that is the end of Rolle's theorem, because we don't really spend a great deal of time on that. It is a special case, and that's nice. But the mean value theorem, that's the one that we do the most with. So let's show you how the mean value theorem works. Just a little bit different from the picture that I drew with Rolle's theorem. But the little difference makes all the difference. I want you to imagine a function starting at A. So this guy here will be f of A. And then this function just does what, functions do, right? It just curves along. It's nice and continuous and differentiable, right? Just like Rolle's theorem, right? Continuous, differentiable. And it finishes at B. Oh God, she's under there again. I'm going to have if I lose control, or my picture, my little puppy is the one that just did it, because she is in here being a pain. You go over there, young lady. No. She's recovering from her operation, and she's using the fact that I can't be too severe with her to get away with blue murder. That's what she's doing. She knows what the heck's going on. Anyway, there we are. So the mean value theorem says the following. If your function is continuous, that's just short for continuous, on the interval AB, and that's short for differentiable on the interval AB, technically curved, but we can live with that. Then there must exist at least one value of x called C that has the property that the derivative of that C is equal to, and you might not have seen this coming, f of B minus f of A over B minus A. So the mean values theorem says that there's at least one point on that curve where its derivative is equal to this fraction. Now you might say, I wonder where this fraction comes from. Let me show you. If you join the start to the finish, see that green line? If I add a couple of extra dotted lines from there to there, do you know the slope of that green line is f of B take away f of A, which is the rise over the run. So according to the mean value theorem, there's at least one place on that curve that has the same slope as this line here. Now, just going with judgment call, that guy has probably got a derivative about here, and probably there. maybe a little bit lower there. So that would be an example of my C, right? It's called the mean value theorem. Are we good? So the questions kind of take the same format. They'll give you a function with an interval and they'll say, is it okay? Can you use the mean value theorem? And then if you can, you then use it to find the missing C. So let me see what question that starts at 5. So in question 5, we have a cubic function, which is that guy. And it's going to be on the interval -2 to 2. I'm not going to write this one down. Is this function continuous for values of x in this range? Yeah.
Yes.
All, and aren't they all differentiable? You kind of don't prove it. Pretty much every function you're going to look at, except weird ones like piecewise functions, right? They might have a problem with being continuous, right? Or vertical asymptote functions, right? You know, certain fractions that are vertical asymptotes. They're going to be the only two that are likely to cause you problems, right? They don't obey the rules, right? They're probably not continuous or differentiable, but these two are. So now I need to find the value of this guy. So it's going to be, that's like A and B. The value of the function at 2, take away the value of the function at -2, and 2 take away -2. So let's see what we get here. I should try that in my head. It's almost dangerous with me, but 2 cubed is 8. Take away 3 lots of 2, which is 6, so gets you 2. 2 add 5 gets you 7. Right, try -2. That's -8, 2, 4, 8, yeah. Add 6 is -2. Add 5 to that and you get 3. Oh, come on. That's far too nice an answer. Right, 1. So f of b, take away f of a, all over b minus a is 1. Then by the mean value theorem, shouldn't there be some place where the derivative is equal to 1? So we're not trying to find when derivatives are 0. We're trying to find when derivatives are equal to whatever this comes to. Well, if I differentiate this function, I get 3x squared take away 3 equals 1. And now we are on the, solving an equation. Okay, as long as you do it to both sides, it's okay rule. That's what kicks in here. Anybody want to suggest what you could do to both sides here?
Add 3.
Oops. What should I do next?
Divide by 3.
Yeah. It would be nice if that was a nicer number, you know, like 4 divided by 2 or something, but it isn't. I'm running short of room, so I'm going to squeeze it up here. What do you do to both sides next to find x?
Square root.
So positive square root. And I wish I had more room. Negative square root. Great. And we call these numbers C. So in WebAssign, you're going to have 2 answers. Do you think I'm going to leave it? I think I'm going to leave it looking like that. Do you think we would consider that a good version of the answer? Can we make a little bit of style points on it? Make it look prettier? What could you do with this?
Like rationalize the denominator?
Well, you could certainly do that, but wouldn't you have to break it into 2 pieces first, right?
Oh,
then
you
you
can do the 2 on top. Yeah,
yeah.
and then you could rationalize it if you wanted to.
And if you wanted to, you would rationalize it. And that would be the pretty version of the answer. That is ugly, that is pretty, and Webasine, because it's not as nice as I am, will take that answer as well. But I doubt it will take this one. I hope it doesn't. So this answer or this answer would be correct. So you would be writing in that guy and minus that guy. So when you get a mean value theorem, at least the early ones, your job is just to find out who these values of C are, right? The special X coordinates where the mean value theorem works. So try our next one. Not the worst looking function in the world. Looks like that. Now, 1 over x does have a problem at 0. Agreed, there's a vertical asymptote at 0, but we're only interested in what it looks like from 1 to 5. Would you agree that this thing is continuous and it's differentiable as long as you're only picking numbers in the range 1 to 5? So we can call that good. That's A and that's B. So the function at 1 is 1. And the function at 5 is a fifth. So I'm now going to find what this is equal to. So it's 1/5 take away 1 over 5 take away 1. I'll just rewrite this again. And I'll let the calculator figure that out. So 1/5 subtract 1 divided by 4. And then if you hit the math button and choose option 1, it'll turn it into negative a fifth. So we are essentially trying to find when is the derivative equal to this guy. So far, so good. Now that means I need to differentiate that guy and put the answer here. If I wanted to differentiate this guy, it's a good idea to call it x to the negative 1. Because then when you do differentiate it, you will eventually get that guy there. So the derivative of 1 over x is negative 1 over x squared. And you can check that, but it is. Right? Differentiate that and then do style points. Solve for x, and the question is over. Any suggestions about algebraically how I'm going to solve this one? And we're going to have to solve it, so what would we do?
Multiply by negative 5x squared.
That is an interesting way, and yes, that would work. Or I could just cross multiply. What you said is fine, and it does work. And if you do a cross multiply, you get x squared and a 5. Can I just pretend the x's disappear, the minuses disappear because each of them are minus, right? So, you know, multiply both by -1 if you want. Now, this gives me two answers. It gives me a plus square root of 5, and it gives me a negative square root of 5. And that's our answer, sort of. Can I put both of these in as a solution to the mean value theorem puzzle? Or does one of them get kicked out for some reason?
The negative one gets kicked out.
And so that's the only answer that you would write in. So in the mean value theorem questions of this type, isn't your job to essentially find the x coordinate that gives you a derivative equal to this fraction. Any questions so far, or is this process okay? Okay. Well, there's only one more of that type. And then we do kind of puzzles for these cells. So the last one of this type is question 7. And we have a log function, but we're sticking to the numbers 1 to 5. So the log function, as long as you keep away from 0, is okay. So it's continuous and differentiable. So I know I can do the mean value theorem. I'm now going to find the value of this fella. Well, it's going to be the value of the function at 5, take away the value of the function at 1, over 5, take away 1. So it's going to be the natural log of 5, take away the natural log of 1, all over 4. Can I make that prettier? Is there anything in that expression there that you can turn into something nicer? Okay, a little bit more specific. Is there anything you can do to those two logs? Okay, more specific. What is the value of natural log of 1? What number is it? I can feel myself aging here rapidly.
0?
Yes, I wasn't trying to make it hard. Just 0. Right? Natural log of 1 is 0, which means that this can be simplified down to look a little bit prettier, right? So we are trying to solve when is the derivative equal to that guy. Now you're going to make my life much nicer this time, right? What's the derivative of log x?
One over x.
Correct. And our job is to solve for x. I would do a little cross multiply. X times the log of 5 is 1 times 4. And then divide both sides by the natural log of 5. And there's the c that you're looking for. 4 over the natural log of 5. So if I gave you a function and an interval, are you comfortable about how you could do the mean value theorem? Which means prove to me that it's continuous and differentiable, which almost always will be anyway. Find the value of this expression and then solve the problem when is the derivative equal to this thing. So you're going to have to do, whatever, as long as you do it to both sides, trick to solve for x. So we finish with, oops, I better cross off my little list now. We then finish with some applications. And these are the trickiest of all the questions. So let me just show you the question before I do it, so you get used to the way it's phrased. Suppose that the derivative of a function in a given range is always between 3 and 5. So you can imagine a function whose derivative is bigger than or equal to 3, but it's always going to be less than or equal to 5, right? So it lives in a very narrow range. What is the minimum and maximum possible value of that expression. And so you would look at that and you think, that's impossible to find out what that is. You didn't even tell me what the function is, so how do I know what the value of it is? The only thing you've told me is this little thing up here about what the derivative can be. Yet that is actually enough to solve this puzzle. It's kind of sneaky how they do it. Let me show you. Right now, the only concrete piece of information that we have is 3 to 5, right? Now, they did tell me that they want to know what the maximum and minimum value of that is. So they've essentially told me that A is 4 and B is 5. So I'm now going to write down f of 8 take away f of 4 over 8 take away 4. And we know that is going to equal the derivative at some number c. Great. Now this becomes f of 8 take away f of 4 over 4 equals that. And then multiply everybody by 4. And we get that. So I now know that the value of f of 8 take away the value of f of 4 is 4 times the derivative. Right. Now, what do I know about the derivative? Well, I know the smallest number that the derivative can be is 3, and I know the biggest is 5. So that makes f of 8.
Is that the interval then?
What is the interval, Vanessa?
Oh, like
The,
would it,
the
just
interval
means
is from 48.
Oh, okay.
So these aren't the interval, but these two numbers are. So this guy take away this guy. Well, if the derivative, this piece here, if the smallest it can be is 3, then won't 4 times it be 12? And this guy, since the biggest the derivative can be is 5, 4 times the derivative gets me 20. So there's the two numbers that they were looking for. What's the absolute min? That's this one. And what's the absolute maximum? That one. Sneaky. If all you tell me is that, and you ask me to find max and min of that, the mean value theorem actually allows it to be possible. Even although I know nothing about the function, right? It could be a sine function, it could be a cubic. Mathematically speaking, if the derivative is between 3 to 5, the maximum value for every function, right, that works, that's continuous and differentiable at least, the maximum value that this difference can be is 20, and the smallest that this difference can be is 12. I think that's kind of interesting that we can do such a thing. Now, that was question 8. Question 9 was the same idea. It's essentially the same question. Just change the numbers a little bit. And my one is 8 and 3. And these two are, in my question, these are the same, but for you it might be 2 and 7. In fact, let's pretend for a minute that this guy was 2 and this guy was 7. When you got to this point here, wouldn't you just say 4 times 2 is the smallest and 4 times 7 is the biggest, right? That's about the only change you would do. And the rest of the stuff is some videos to watch on essentially the mean value theorem. I think one of them is actually, and takes you through this process as well. Is there anything in that section that you want me to go over? Or are you comfortable with what the mean value theorem does? Last chance. Okay. So let's move on. Math 151. Section 4.3. Derivatives and the shapes of graphs. It's a very visual section. Just get my thing set up. So I'm going to do a fair amount of notes today for what's left the last 10 minutes. So here it goes. I'm going to start down here, -1. We finish there, right? We're going to have that guy at 0. This guy can be at 5. This guy here is at 10. There. And we're going to look at intervals where a function is increasing and intervals where a function is decreasing. So this function starts off at x equals -1, finishes at x equals, say, 15, and it goes up, it goes down, it goes up, has a funny little cusp shape, and goes back down. Now, when we talk about a function that is increasing, I always want you to read it as if you're going from left to right. Now, in this function here, you are increasing to there. And so from -1 to 0. So that's an interval, right? From x equals -1 to 0, this function is increasing. Can someone tell me another interval of x where this function is increasing?
5 to 10.
Would you agree? And the way I think of it is, if you travel from left to right and you're going uphill, you're increasing. Does that help, right? So you're traveling from left to right. That's why my little arrow here is. You're increasing. And we do a little union symbol and 5 to 10. So that's values of x from -1 to 0 and values of x from 5 to 10. That's essentially what that notation is telling me. Now, if you want to talk about decreasing, then would you agree that in this case, the function is decreasing going downhill from here to here and from here to here, and from 0 to 5, right? So for values of x from 0 to 5, the function is decreasing, and from 10 to 15, it's also decreasing. Now, this particular one, I started at x equals -1, and the graph just abruptly finishes at 15, and that is common. But suppose you put an arrow at the end. What that is indicating is that this graph just keeps doing what it's doing forever. How will that affect this interval here? It won't be from 10 to 15 anymore.
I've got a 10 to infinity.
Yeah. So you may have to put infinities. So how do I know if I've got an infinity? How do I know if I've got a start and a finish? If they have a start and a finish, don't they normally do a little dotty thing here and a little dotty thing here? And when it goes on forever, don't they put a little arrow at the end of the curves? So if you see arrows, it's going on forever. If it has a nice dot, that would be nice. But if there's no arrow, you'll assume that there's a dot there and it stops. Are we good with that? Right, now, things are getting a little bit messy because my picture's got a lot already in it. But we're now going to use terms I don't think you've heard before. Concave up and concave down. If a curve is concave up, it looks like a happy face. It's even allowed to be concave up if it only has half a happy face, right? Only has one side of the smile. A thing is concave down if it is a sad face shape. Even if it's only half a sad face shape, it is called concave down. Now, curves are typically concave up or concave down. The only time they are neither is if it's a straight line, right? Would you agree a straight line's not going up or down, right? You can't see curvature in it. Now, this shape has a concave down going on. Would you agree here? Can you see if I cover that up? Can you see a sad face? Concave down. On the other hand, next to it, if I cover all the stuff that's a distraction, would you see there's a happy face? So isn't there a concave up also happening? So things are going to get a little bit messy, but here goes. I want to know for what values of x is this shape concave up? And I want to know when it's concave down. Well, the problem is that almost every concave up eventually turns into a concave down. So can you see I've got a concave down here turning into a concave up? So isn't there some little point roughly about where my pen is, where the transition happens? Because you're not allowed to be both, right? You must be part of a concave up or you must be part of a concave down. Now, since I don't have any clues, would it seem reasonable that I pick halfway? Halfway from the hill to the valley. Does that seem a reasonable place where the changeover happens? So this shape is concave down from x equals -1 to x equals 2.5. And that's a concave down. Okay. Here is my happy face. It starts at x equals 2.5, right? There's my concave up, my happy face. In this shape, what value of x does it finish being a happy face? It finishes being concave up.
10.
At 10. Because of this little guy here called a cusp, isn't it all happy, right? There isn't a transition going on. So I told you it would be a little bit tricky. There we go. So concave down, turning into concave up. This little guy at the end, which I'm going to now say it continues like this for infinite. This little piece at the end, right? You must be concave up or concave down, right? You're not allowed to be both. What's that guy? Part of a happy face or part of a sad face? Because that tells you if he's concave up or concave down.
I guess be concave up forever.
Yeah, forever. So from x equals 10 to forever. So when you are looking at a shape, right, and you're being asked for what values of x is it concave up and it's concave down, don't you have to make sometimes a little judgment call about where the transition happens? And the best way I do it is look at the bottom of the hill, look at the top of the hill, and pick halfway between it. That seems to be a reasonable point to choose. Unless you've got a nice little cusp like that. So far, so good. Now, one last feature is called the point of inflection. Points of inflection only happen when there is a transition from a concave up to a concave down, right? For instance, here, we have a concave down turning into a concave up, right? And that is the guy that is called the point of inflection. And you write down his x coordinate, and let's assume that that's 11, and its y coordinate. So you actually give the point, right, the coordinates of the point of inflection. Now, is this guy here a point of inflection? Well, isn't it a happy face turning into, oh, another happy face? Points of inflection only happen when there's a changeover, right? So happy turning into sad, sad turning into happy, right? If you have a happy face turning into another different happy face, it's not a point of inflection. So that is not a point of inflection, yet this is. Does that make sense? The difference between the two is a concave up changing into concave down is a point of inflection. A concave up turning into a different looking concave up is not considered a point of inflection.